Welcome to this 12th and last lecture in this special version of the Discrete Optimization Master Course this year. Well, did I say last lecture? Yeah! So what I'm going to do in this lecture is two more things that I hope you still like to see in discrete optimization, namely in coping with NP-hard problems. And the first of these two things has to do with the power of randomization in the design of approximation algorithms. And I'm going to do that on the example of the maximum satisfiability problem. So what is the maximum satisfiability problem? Well, we are given, just like in the regular satisfiability problem, an instance of SAT. So that is a formula in conjunctive normal form. So the conjunction of m clauses on n Boolean variables. But the question now is, well, how many of these m clauses can I satisfy at least? Okay, so maybe not all of them can be satisfied, then we would have a yes instance of the SAT problem, but how many of the clauses can I satisfy at least? And the first simple theorem says, well, there always exists for any satisfiability instance a truth assignment satisfying at least half of the clauses. And the proof of that is surprisingly simple. We just do the following. We pick any variable independent of each other. So xj, I let xj to be true with probability 1/2 and false with probability 1/2, all independent from each other. Then I can argue that the expected number of fulfilled clauses is at least half the number of the total number of clauses. So at least 1/2 times m. So how do we see that? Okay, so let's have a look. Why is this true? What we do is we define a random variable xi, one for each of the clauses ci, which is equal to 1 if the clause is true and equal to 0 otherwise. Now, by definition, the expected number of fulfilled or true clauses is just the expectation of the sum of these m random variables. And by linearity of expectation, this is equal to the sum taken over all the clauses. And then we have the expectation of this random variable xi. But what is this? This random variable xi is 1 if the clause is true and 0 otherwise. So this is just the probability of the clause being true or of the random variable being equal to 1. So this is the sum taken over all the classes of all these probabilities for the individual random variables. And now I claim that the probability for a clause being true is at least 1/2 for each of the clauses. Why is that? Well, suppose the clause only contains one literal. Then remember the truth assignment, which sets a Boolean variable to be true and false with probabilities 1/2. So then the clause with just one literal is true with probability 1/2. If the clause contains 2 or more literals, then the probability for the clause being fulfilled is even larger, right? Because the clause is just a disjunction of several literals. So for the clause to be true, only one of the literals needs to be fulfilled. Okay, so this probability is at least 1/2, and hence the total sum of all these 1/2 probabilities is at least 1/2 times the number of clauses. So if I may be a bit more specific, so the probability for a clause to be true, right, is just 1 minus the probability for the clause being false. And when do I falsify a clause? Well, that's just this one specific truth assignment, which makes all the literals to be false, which happens by independence of the probabilities with setting the Boolean variables to be true or false, which happens with probability 1/2 to the number of literals in that clause, right? And obviously this is at least 1/2. So if the number of literals is exactly equal to 1, and otherwise it's even larger. Okay, so we showed that the expected number of fulfilled clauses is at least 1/2 times the total number of clauses when we do a random truth assignment. But if the expected number is that large, of course, there must exist at least one truth assignment, which is at least as large as 1/2 times m. Otherwise, the expectation can't be that large, right? So we have existence of a truth assignment fulfilling at least half of the clauses. And as a matter of fact, our proof even showed a little bit more. Namely, if we have at least k literals in each of the clauses, so k is a lower bound on the number of literals per clause, then the expected number of fulfilled clauses is at least that large. So 1 minus 1/2 to the k times the total number of clauses. And I just argued why this is the case. So just to give an example, if we talk about the 3 satisfiability problem, where each clause has exactly 3 literals, that means that the random truth assignment achieves almost 90% of the clauses being fulfilled, or in other words, there exists a truth assignment fulfilling almost 90% of the clauses. And the proof I just did, right? So if a clause contains li literals, this clause will be false with probability 1/2 to the li, which, because k is a lower bound on the number of literals, is upper bounded by 1/2 to the k, and hence the expected number of true clauses is at least as large as 1 minus 1/2 to the k times the total number of clauses. So random truth assignments are good in expectation, but for which problem actually? And let's be a little bit more formal here. So let's define this problem that we are talking about as maximum satisfiability. And that is the problem given a formula f in conjunctive normal form, find a truth assignment x maximizing the number of fulfilled clauses. Okay, so this is an optimization problem, a discrete optimization problem known as max satisfiability. It is NP hard because only the decision version, does there exist a truth assignment fulfilling all of the clauses? That's exactly our NP complete satisfiability problem, right? And if it's NP hard, it's also immediately strongly NP hard because this is a problem that doesn't even involve any numbers. So for this discrete optimization problem, we have a good algorithm in a certain sense. What we have is a randomized algorithm, namely which sets variables, Boolean variables, to be true or false, each with probability 1/2 and independent from each other, right? So assuming that this randomization can be done in constant time, this is even a linear time algorithm, and it produces a solution x, of which we can say, well, it's at least good in expectation, right? So the expected number of fulfilled clauses for this x is at least 1/2 times the total number of clauses in the instance. And of course, the total number of clauses, that's the maximum we could achieve anyhow. So the optimum solution, so the maximum number of fulfilled clauses in an optimum solution cannot be more than m, obviously. So we have a 1/2 approximation, but only in expectation. So is that any good? Well, yes and no. It's not that good because if I run this algorithm once, I could get a truth assignment which is much, much worse than this expectation, right? So I would have to run this algorithm many, many times in order to find a truth assignment which is as good. And the main question now is, well, given this randomized algorithm, can we also find a truth assignment x just in polynomial time which achieves the same bound? And the answer is yes. And that boils down to the question, given this randomized algorithm, can we de-randomize this algorithm? So can we come up with a deterministic algorithm while preserving the same approximation guarantee, 1/2? And that is true, and that is actually true for very many randomized algorithms and known as the method of conditional expectations. And that works as follows. So let us look at x, which is the random variable which denotes the total number of fulfilled clauses by our algorithm, and that depends on this random truth assignment of the Boolean variables. By Bayes' law, I can write this expectation as the sum of two conditional expectations, namely that is 1/2 times the expected number of true clauses or fulfilled clauses under the condition that the first variable is equal to true, plus 1/2 times the same thing under the condition that the first variable is set to false. And the nice thing is that I can not only split up the total expectation in this way, I can also compute these values here in polynomial time. And why is that true? Well, the reason is that I can write down the whole expectation, so the expected number of fulfilled clauses, as the sum, and we have seen that earlier, of the probabilities of each clause being true. So let's look at a concrete example here. So let's look at this clause Ci, which is x1 or x2 or not x7. Okay. So how can I compute the probability of this clause being true, say under the assumption that the first variable x1 is true? Well, the only thing I have to do for a given clause Ci is I have to go over or look at the literals that are contained in the clause, right? So for instance, if I want to compute the conditional probability for the clause being true under the assumption that the first variable x1 is set to be true, then since the variable x1 appears in the clause, I see that the clause will be fulfilled, and hence this conditional probability will be 1 because it's independent on the truth values of the other variables, right? Likewise, if I want to compute the complement probability that the clause is true under the assumption that x1 is false, I see that x1 is not fulfilled. I have two still random variables here, right? I mean, x2 is not yet fixed, x7 is not yet fixed, and there is 4 possible truth assignments for these two variables here, 3 of which will fulfill the clause, and hence the probability for the clause being fulfilled under the assumption that x1 is false will be 3 over 4, right? So it boils down to a simple counting argument of the number of free yet undetermined literals that appear in this clause here, of course, given the fixed values that I assumed here, given the fixed truth assignments for these for x1 in this case. And now, since each clause contains at most n literals, this computation here in general will take order n time. And in total, I would have a computation time of order n times m, because I will have to compute all these probabilities for all the m clauses, right? And specifically, for example, for the 3 satisfiability problem, computing these conditional probabilities would take constant time because the number of literals is just 3, right? So for the 3 satisfiability problem, the computation of these conditional expectations just takes time order m, where m is the number of clauses. Now that is nice. I can split up the total expected number of fulfilled clauses into these 2 conditional cases. And now the nice thing is this. Now I have computed these values, 1 and 2, in polynomial time. I can just compare them and pick the better of the 2. Okay, so the larger of the 2, since we want to maximize the number of fulfilled clauses. So if the first conditional expectation is larger than the second, then that means that this conditional expectation is also larger than the original expected value with which I started, right? And then I just fix the first variable to be true, and otherwise I would fix the first variable to be false if the inequality here would point in the other direction. So assuming this first conditional expectation was larger than the other one, we just keep this value, the truth assignment of the first Boolean variable, to be fixed, and we continue with the next variable, variable number 2. So now I would compute the conditional expectation, so the expected number of fulfilled clauses under the assumption that the fixed variable x1 is true and the variable x2 is also true. And I would also compute the same thing under the fixed assumption that x1 is true and x2 is false. And again, I just compare these 2 conditional expectations, and I fix variable number 2 according to the larger of these 2 expressions, right? So keeping then Boolean variables x1 and x2 fixed, I do the same with x3, and so on and so on. And at the end, I will have computed, right? I'm fixing one variable after the other. So I will have computed a fixed truth assignment, x, fulfilling at least as many clauses as we started with. So at least as many as the original expected value here, right? And that was at least half of the total number of clauses. And what is the computation time? Well, each step, so each computation of these conditional expectations takes time order n times m. I fix n variables, so I have n iterations of this de-randomization, and the total computation time is indeed order n squared times m, which is polynomial. So all that can be nicely illustrated by, say, one more concrete example. So here we have an example where we have in total 10 clauses. So each row of this matrix here contains a clause. So we have clauses of length 1, clauses of length 2, and so on. And in this column of the matrix, I just wrote down the expectation of this clause being fulfilled for a complete random assignment. So for the clauses of length 1, that would be probability 1/2. For the clauses of length 2, that would be probabilities 3/4, and so on. Okay, so the expected number of fulfilled clauses for this instance for a random assignment would be something close to 7. Now I compute the conditional expectations under the assumption that either x1 is false or x1 is true, right? And in order to do that, I have to compute the conditional probabilities of clauses being fulfilled for each of the clauses under the assumption that x1 is false and x1 is true. And then the sum of all these entries here gives me the expected number of fulfilled clauses if I have x1 fixed to be false and all the other variables still are assigned with random with probabilities 1/2, right? So that would be 6.5. And under the assumption that x1 is true, I get a 7.3. And then, of course, I would continue with this larger of these two conditional expectations, which, if you compare, is indeed larger than the 6.9 that we started with. And we would fix variable x1 to be true. And the next step would then be to do the same, keeping variable x1 to be true, right? I compute the two conditional expectations, x2 being false or x2 being true. I do it exactly in the same way. And here I see that fixing variable x2 to be false gives me the better of these two conditional expectations. So this is what I do. And this way I just continue. And if you look at this matrix or this construction, you can also immediately see how you arrive at the computation time, right? I have here m clauses. Computing each of these entries here is computing a conditional probability of the clause being fulfilled, having some of the truth assignments fixed and some still probabilistic, and that takes linear time in the number of literals, and that is at most n literals per clause, right? So this whole table would continue in this direction for n iterations. Once all the variables, all the n Boolean variables are fixed, we are done, right? So we have each entry in this matrix costs me order n time to compute. I have m rows and I have n columns, so that gives me the computation time order n squared times m. Here is another illustration or complete illustration of the situation, right? You can also think of it as a decision tree. Here in the root, everything is still a random assignment. And now I start fixing variables one by one, fixing x1 to be false or x1 to be true. I pick the larger of these two conditional expectations. And this way, at the end, I will have fixed all the variables. Okay. And indeed, by construction of the whole argument, the number of fulfilled clauses by the fixed truth assignment that I have achieved here, which is x1 true, x2 false, x3 true, x4 false, that fulfills 9 of the 10 clauses, and this 9 is at least as large as the original expected number of fulfilled clauses under the random assignment. And this method of conditional or de-randomization of a randomized algorithm by conditional expectations, that works for very many discrete optimization problems. Okay, so that already finishes the first half of this lecture, this final lecture. So what did we do? We had a randomized algorithm on the example of the maximum satisfiability problem, and we were able to de-randomize it into a deterministic algorithm achieving the same performance guarantee. And I would like to at least mention that randomization is in general a very powerful tool in the design of algorithms, in particular when we look at the worst case behavior of such algorithms, right? So you can maybe intuitively imagine that if I use a randomized algorithm, it is much more difficult to trick the algorithm into a worst case instance. And hence, it can happen that we can achieve expected performance of a randomized algorithm quite easily. And then if we afterwards succeed in de-randomizing this randomized algorithm into a deterministic algorithm achieving the same performance bound, then we kind of combine the benefits of two worlds into one, right? Now, for the final part of this lecture, I would like to concentrate on what is known as approximation schemes. So this last part of the lecture, or the series of lectures overall, we are going to drive this idea of designing approximation algorithms to the extreme in some sense. And the motivation is this. I mean, suppose you have designed your approximation algorithm, some alpha approximation algorithm for your favorite NP-hard optimization problem, great, for some constant alpha, but the question really is how far can you go? So can you maybe, by designing an even more clever algorithm, get a smaller approximation guarantee, as close to 1 as possible? And the best we can hope for, unless P is equal to NP, because we are still talking about an NP-hard optimization problem, would be an algorithm that comes as close to the optimum solution as you want. Okay, so that would be a 1 plus epsilon approximation algorithm for arbitrarily small given epsilon. So you tell me my algorithm should not be worse than 10% of the optimum solution, then this epsilon would be equal to 0.1, and I would have a polynomial time algorithm that achieves this performance guarantee. And that leads to the definition of so-called PTASes, so a polynomial time approximation scheme. So as usual, in the following, pi is the problem we are talking about, I is an instance, and this is the corresponding, say, binary encoding length of the instance, some succinct, efficient encoding scheme, and I refer to the encoding length of the problem also as n in the following, okay, for simplicity. And then the definition of a polynomial time approximation scheme, PTAS, that's a family of algorithms parameterized by this desired precision. So how close you want to come to the optimal solution. This precision parameter epsilon here, and a epsilon for any given epsilon is a 1 plus epsilon approximation algorithm. So it always computes a feasible solution, which is not worse than 1 plus epsilon times the optimum solution value. And of course, then by definition, the computation time should be polynomial in the encoding length of the problem for each epsilon. And notice that this definition still leaves room for computation times, for instance, of the order n to the 1 over epsilon. So I do not require the computation time to be polynomial in the precision that I require. It only has to be polynomial in the encoding length of the instance. So just for instance, if the precision, the required precision, would be equal to 1 over n, then this computation time would be n to the n, which is no longer a polynomial, okay? So n to the 1 over epsilon would be a polynomial function for any fixed epsilon, but it's not a polynomial in 1 over epsilon. All right, if we also require that, that leads to the definition of a fully polynomial time approximation scheme. And that is just exactly the same, with the only difference that I also require the computation time to be polynomial both in the input size of the instance and the precision that I require, so in 1 over epsilon. So here, for an f-PTAS, it is not okay to have this computation time n to the 1 over epsilon, because this is not a polynomial function in 1 over epsilon. But it would be okay, for example, to have this polynomial. So it depends polynomially on n squared, which is the input size of the problem, and also polynomially in the required precision, right? So if epsilon would be 1 over n here, that would be the polynomial function n to the 4. Okay, but how do we achieve such a miracle, an algorithm that comes as close to the optimum solution and that also in polynomial time? And the basic idea is typically that we are rounding the input instance, which the rounding somehow depends on the precision parameter that is given, such that after the rounding, my problem becomes polynomial to solve. In an illustration, this would look as follows. So here we have our difficult instance. It almost looks a little bit like a ghost. And we have this rounding parameter epsilon, by which we round the input instance into something that has much more structure, right? So this looks already much less than a ghost. And this instance here becomes polynomial time solvable. So we can compute the optimum solution on the rounded instance. And then the challenge or the clever step is to transform this solution back into a solution to the original problem here without any rounding, such that this solution is very close to the optimal solution. That's the idea. So for any given epsilon, this would be polynomial time solvable, but in the limit when epsilon is equal to 0, this instance would just be the same as that one here, okay? And I'm going to explain this idea, this rounding idea, on one example, and that is going to be for the knapsack problem. And as a matter of fact, we already had an algorithm to solve the knapsack problem optimally, but for this purpose here, I would like to introduce yet another algorithm to solve the knapsack problem optimally. So just as a reminder, what was the knapsack problem? We have items 1 up to n. They have weights, right? They have profits, and I have large W, which is the knapsack size. And I want to collect items that fit into the knapsack, so the total weight is at most this large W with maximum total profit. Let's define P, this capital P here, as the maximum of all the profits. Then, of course, any feasible packing has a profit at most n times P. So n times P is an upper bound on the optimum solution value that we might achieve, right? And now I solve the knapsack problem by the following algorithm, which is called a dynamic programming algorithm, by using the following notation. So for every index I going from 1 up to n, and for every profit value, little p here, that will range between 0 and this upper bound n times p, I define these numbers here, AIP. What is AIP? Well, that's, first of all, that's a subset of items taken only from the items 1 up to I, whose profit, so the sum of the items in S, the total profit P of S, is exactly equal to P, this parameter P here, okay? And among all such subsets, if there are several, I take one with minimum weight. So this denotes the minimum weight with which I can achieve profit exactly equal to P. And that only restricted to items 1 up to A. If there is no subset that achieves exactly a profit P, this value will be set to plus infinity, okay? Now, how can I find back the optimum solution value? Well, the optimum solution value, that will be the maximum profit such that the total weight is at most W, right? So that would correspond to a subset that still fits into the knapsack and achieves maximum profit. And notice that here in this definition, I take ANP, which means I'm allowed to select all the items up to N. Let me explain that in a little illustration, so that I think helps. So I write down this whole huge matrix of all these values, AIP, where remember that AIP, well, that was the minimum weight to achieve a profit value exactly P, restricted to only taking items 1 up to I. Now, if this index I here is equal to N, that means I'm allowed to take all the items. So if I look at the very last column here, that would be all the values, that would be the minimum weight subset from taking all the, allowed to take all the items 1 up to N to achieve a profit of 0, of 1, and so on and so on. So the optimum solution value will be the bottommost value where the weight is still smaller or equal than W, okay? So here in this last column, that would correspond to subsets of all the items 1 up to n. And I would have the profit values increasing in this direction, right? And here the entries would correspond to the minimum weight with which I can achieve the corresponding profit. So I would like to have the bottommost value, that would be the maximum profit, but I have to restrict to total weight being at most W. So the bottommost value, which is smaller or equal than this capital W, that corresponds to the optimum solution. Okay. So if that happens in the pth row for some small p here, then p is the maximum profit with which I can achieve a total weight at most W. Okay. Now let's briefly look at the dimensions of this huge matrix of numbers. So here I would have, I'm ranging from 0 up to n times p. So I would have n times p columns, rows of this matrix, and I would have n columns in this matrix. So the total number of entries is n squared times p. And remember, this capital P was the maximum profit value among all the items. Okay. So knowing that I can compute the optimum solution value, once I have filled or have computed all the values here in the last column of this matrix, the question is, how do I compute these values? How do I fill this matrix? And the main idea here is to fill this matrix column by column. So starting with the leftmost column and then working towards the rightmost column. Okay. And the main idea in dynamic programming is this: how do I compute this value or the next value, let's say? Okay, so here, how would I compute? Once I have already computed, say, all the columns 1 up to A, how can I compute an entry in the column number I plus 1 here? Okay. And if I can only compute, or if I can compute this value here by only looking up some values that are already pre-computed before in the columns 1 up to I, then I'm in shape, right? Because then I can just simply compute this value here and fill the corresponding column, and then I iterate over all the columns of the matrix. And that is the idea. Of course, the computation of this entry here should still be polynomial in all the values that I pre-computed earlier. But that is actually possible, because remember what this I plus first column stands for. That means in comparison to the previous column here, I'm now allowed to also include item number I plus 1. Whereas in this previous column, that were all the subsets up to item I, and now I'm also allowed to include an additional item I plus 1. And actually there's only two cases. Either I include this item I plus 1, or I don't include it. So that will be a very simple calculation in order to get this value here, this minimum weight, given all the pre-computed values in the previous column. So that's the idea of dynamic programming. So let me explicitly explain how we can do that. Okay, so first of all, one word on how do I start, how do I initialize these columns of the matrix. And the first thing to observe is this. So when I look at values A1P, okay, so that means I'm allowed to take item number 1 or not. So which profit values can I achieve with only item number 1? I can only achieve profit value P1 of that particular item. Okay, and what is the minimum weight to achieve that profit P1? Well, that's the corresponding weight of the item. So in order to fill the first column of this matrix, I set A1P1 equal to the weight of this item number 1, and A1P will be plus infinity everywhere else for all profit values larger than 0 and not equal to the profit of that particular item. And if I can also fill the topmost row of the whole matrix, because in order to achieve the topmost row corresponds to profit values equal to 0. So that just means I take no item at all. And the minimum weight to achieve profit 0 is also weight 0. So the topmost row of the whole matrix will be just filled with zeros. Suppose now that we have already computed all the columns 1 up to I in this matrix. So how do I get entries in the next column? So how do I compute these entries A, I plus 1, P for a given profit value P? Well, as I said, there is two cases. Either I can include this item or I can exclude this item, right? So if I exclude the item I plus 1, then that just means that under the condition that I exclude this item, I just have a subset of the items 1 up to I. So then under this condition, the minimum weight to achieve this profit value P, that is just exactly what I computed in the previous column, right? So that is the minimum weight of all the items 1 up to I in order to get a profit exactly P. So then I just copy this entry from the previous column in the matrix. And under the condition that I include this I plus first item, then I know that in order to achieve a profit P with all the remaining items 1 up to I must achieve a profit P minus the profit of that item that I have to include now, right? So that would be, so this value here would be the minimum weight to get the profit of P minus the profit of the I plus first item. So that would be the minimum weight to achieve that profit. And of course, I'm adding item I plus 1, so therefore I have to add the weight of item I plus 1 to this total weight here. Okay. Let me explain that in this figure here. So here I have an item which has a weight of 5 and a profit of 3. So item number I plus 1 has a weight of 5 and a profit of 3. So if in the minimum weight subset, in order to achieve a profit exactly P, I do not include this I plus first item, I can just copy the entry from the previous column, which was already representing the minimum weight to achieve profit exactly P, only taking items 1 up to I. If on the other hand, I want to include this I plus first item, okay, then in order to achieve this profit value of P, since the profit of this item is 3, I look into the table, what was the minimum weight to achieve a profit 3 less? Okay, so this was the minimum weight to achieve a profit P minus 3. And then I take this weight and I add the weight of item number I plus 1 to that number, and that would give me the corresponding entry here. And as a matter of fact, since I do not know if I should or should not include the item, of course, I have to take the minimum of these two values in order to get the right entry in this matrix here. But that means in order to compute the correct entry in the I plus first column of the matrix, I just have to look up two entries in the previous column, in the ith column of the matrix, and take the minimum of the two corresponding values, right? So that means in order to compute this value here, I just have to look up these two values and make a minimum computation. So that's a constant time operation. So here is once again the summary. So the I plus first entry for a given profit value P is just obtained as the minimum of these two values, and that is a constant time operation, right? So, but that means we can fill the whole matrix by just going over the entries column by column and top from bottom and compute all the entries in the matrix for all the corresponding profit values P in the size of the matrix, which is n squared times capital P. And just remember, this capital P was the upper bound or was the maximum profit value among all the items. So maybe it pays off to look at a small example here. So here we have an instance of the knapsack problem where the knapsack capacity would be 4. So these horizontal lines would be the dimension in terms of capacity. Then we will have an item number 1 here, which has a weight of 2 and also a profit of 2. We have item number 2 here with a weight of 1 and a profit of 2. And we have this third item with a weight of 3 and a profit of 5. Okay. Now, we built this whole matrix, which in principle has n columns and n times p rows. But as a matter of fact, if I, for example, sum up all the profit values, that is certainly an upper bound on the maximum profit that I can achieve. That would be 9. So this table here goes up to 12. That is certainly more than sufficient. Okay. Okay, so let's start filling the matrix. And since the first item here has a profit value of 2, I can only achieve a profit of 2 with that item, right? So therefore, I have an entry here which is not plus infinity, so I can only achieve a profit of 2, and the corresponding weight is 2, and therefore we have this 2 here. All the other entries are plus infinity, of course, except for the top row, which corresponds to not taking item number 1, and that would be a profit of 0, obviously, and a total weight of 0 as well. Now let's start filling the second column of this matrix. And as a first observation, the second item also has a profit of 2, right? So a profit of 1 cannot be achieved, and hence I get a plus infinity here in the corresponding entry of the matrix. And now the first interesting happens. If I want to achieve a total profit of 2 using items 1 and 2, or 1 or 2. All right, and you already see that the minimum weight in order to achieve the profit of 2 is obtained by taking item number 2 and not taking item number 1. So in terms of calculation in this matrix, that would mean, well, I take the minimum of 2 entries. First of all, the minimum of this 2 here, that would correspond to not including item number 2 and still having item number 1 included. Or I do include item number 2, and that would be this entry. Item number 2 has a profit of 2, so therefore I look, in order to achieve a total profit of 2 and including item number 2, with the remaining items I have to achieve, or I have to add up to profit 0, right? So therefore I look in this matrix in 2 rows above the current row that I want to calculate. So that is the 0, and the 0 plus 1 for the weight of item number 2 gives me this 1, right? The minimum computation would be, it is down here, it would be the minimum of 2 here and the 0 plus 1 here, right? So that would be the 2 here, and that would be 0 plus 1 here. And that would be this minimum computation, and obviously 1 is smaller. So therefore I have a 1 here. And so it continues, right? So the interesting entries are here. So for example, to achieve a profit of 4, I would actually include both items, and that gives me a total weight of 3. So I see this 3 here, which has been obtained by including item number 1, and in addition also including item number 2, which has a weight of 1. And that's it, right? So all the other entries are plus infinity. And then we continue filling the final column of the matrix. I'm not going over all the calculations again. So this would again correspond to not including item number 3 here in order to achieve a profit value of 4 and 2. And indeed, this item here is a profit value of 5. So therefore, this is the correct values here as well. Now, the only way of achieving a profit of 5 here would be to include item number 3 at a weight of 3, right? And so on. So I fill all the other entries of the matrix in exactly the same way using the simple minimum calculation. And then I can look up in the last column of the matrix which is the bottommost entry, which still has a weight at most 4, and that would be actually this one here, corresponding to a total profit of 7. Indeed, if that would be the minimum weight to achieve, this one here, profit of 7, that would be achieved with a weight of 4, namely by including item number 3 and item number 2. What you can also see is that this profit of 9 here cannot be achieved because of the fact that the total weight would sum up to 6 here. So indeed, 4 is the minimum weight in order to achieve maximum profit of 7. All right, so this dynamic programming algorithm is another algorithm to solve the knapsack problem, But that is actually not what I wanted to do, right? Now we have an exact algorithm to solve the knapsack problem again. We had one earlier in this course. The computation time of this algorithm that I just explained is the size of the corresponding dynamic programming table that I computed, and that was n squared times p. It's obviously not a polynomial time algorithm because it depends on the maximum profit, right? So it's a pseudo polynomial time algorithm for the knapsack problem. So I claimed I wanted to solve the knapsack problem actually in polynomial time, and that with arbitrary precision. I wanted to obtain a polynomial time approximation scheme for the knapsack problem. And what I'm going to do is the following. I'm going to use, I'm going to take the instance, I'm going to round the profit values actually. And then on this rounded instance, I'm going to use this dynamic programming algorithm. And you can already guess what happens. I'm going to round these profit values down in such a way that this computation time actually becomes a polynomial computation time. That's the trick here, okay? And here is the algorithm in more detail. So it's parameterized by the desired precision epsilon. And in order to do the rounding, I define this number k here. This is just epsilon times the maximum profit value divided by n. So that's just a number that works out. I define the new instance, the rounded instance, I prime, by just taking the original profit values, pj, and divide them by k, this constant k here, this number, and I round down, okay? That defines a new instance. I do nothing with the weights. Now I use the dynamic programming algorithm that I just explained to compute an optimal solution on this new instance I prime. Okay. Since I did nothing for the weights, so the weights are still the same, any feasible solution in this new instance I prime is also a feasible solution for the original instance, right? So all the items have to fit into the knapsack weight-wise, and I didn't change the weights. So what I compute by this dynamic programming algorithm is a subset of the items. Let's call it x prime. And that's feasible, okay? And that's the feasible solution that I return. Okay, it's a feasible solution. Now I make two claims. First of all, the solution value obtained in this way is at least as good as 1 minus epsilon times the optimal solution value. Notice that we are talking about a maximization problem here. Hence, a polynomial time approximation scheme approximates the optimal solution from below, right? And second claim, the computation time of this algorithm is polynomial, both in the size or the number of items and the desired precision. So we actually have an F-PETAS, fully polynomial time approximation scheme. So before I prove these two claims to you, let me make one more intuitive remark about what happened with this rounding here. Okay, so what did I do? I rounded down the profit values in some way. So what exactly did I do? I took the original profit value, which was an integer, I divided it by this constant k here, and then I was rounding down, okay? So by dividing by k, I get a fractional number, and then the rounding eliminates all these insignificant bits behind the comma, right? So rounding down to integer effectively eliminates all the insignificant bits, and intuitively I get much less and much smaller profit values now, and that makes the instance easier to solve. And more specifically, our computation time of the dynamic programming algorithm was dependent on the maximum profit value. And now if I look at the maximum profit value of this new instance, by choice of the scaling parameter k here, this maximum profit value is now small. It's now just n divided by epsilon, right? And that will make sure that the computation time will actually be a true polynomial in n, the number of items at the end. Now, having done all that, the actual proof of these two claims is very simple. Okay, so let's have a look. Here I just recall all the definitions that we made, and remember the algorithm just computes an optimal subset x prime on the rounded instance. So that means for these profit values p prime, okay? And let's say, for the sake of the proof, x is an optimal solution for the original instance, so for the original profit values. So that's a subset of the items, and this is also a subset of the items. And in order to finish the argument, I need these two observations. First of all, these two inequalities here, which are just a rephrasement of the rounding, right? So in the rounding, I said, well, the new profit value is pj prime. That's the old profit values divided by k rounded down. And that, of course, means that these new profit values, pj prime, they are in between pj divided by k minus 1 and pj divided by k on the right-hand side, right? And that is exactly, now multiply everything by k here. That is these two inequalities. So that's just the rounding itself. So I can sandwich these new profit values, or k times these new profit values, in between these two numbers. Second observation is this. So this says if I add up the new profit values of all the items in the set x prime, because x prime was an optimal solution for the new profit values, that is larger or equal than if I add up all the new or rounded profit values for the optimal solution. So this was an optimal solution for the original instance. This is an optimal solution for the rounded instance. And here I look at the rounded profit values, right? So therefore this follows by optimality of x prime for the rounded instance. And that's all that I need, actually. So let's see. This is the value that the algorithm achieves, right? It computes an optimal solution on the rounded instance. So that's a subset of items. But this is the original items, right? So the original profit values. Okay. First inequality. Here, the profit value pj is larger or equal than k times pj prime. So that's the inequality that I use here. Okay. Still, I'm summing over all the items in the optimum solution for the rounded instance. Next step. Here, I use optimality of the set x prime for the rounded profit values, right? So that is the second inequality, or second observation up here, because now I exchange x prime for x. So this is just a constant k, which is multiplied everywhere. So x prime was an optimal solution for the rounded profit values. Hence, I have this inequality here. Now I use the other half of this inequality. Okay, so now I get that the number k times the rounded profit values, okay, so that is lower bounded by the original profit values minus k. So hence I get this minus the size of this set x here times k, okay. But notice that this is the optimum solution value, right? So now I have exchanged, in this step here, I've exchanged x prime for x. Here, we just sum up all the profit values in the optimum solution. So this is the optimum solution here. And of course, the optimum solution cannot take more than n items. Hence, I get this inequality here, right? So the number of items here is at most n. So that is certainly, this here is still a lower bound. Now, as I already said, this is the optimum solution. So what I have is, this is the optimum solution value minus n times k. And now you see why we chose the scaling parameter k in the way we did, because n times k, if you have a look up here, the scaling parameter k was epsilon times p divided by n. So n times k is just equal to epsilon times p, okay? So we get that the solution value obtained by our algorithm is at least as good as optimum solution value minus epsilon times capital P. But since by default we assume that all the items, or each individual item, fits into the knapsack, okay, so that's an assumption without loss of generality, this is the profit of the maximum profit item, and the optimum solution can only be better than that, right? I mean, in the optimum solution, we could also choose just the maximum profit item, and then it would be equal to this capital pay, but it can only be better. So this is a lower bound on the optimum solution, and hence you already see what is going to happen. So therefore, all this here is lower bounded by 1 minus epsilon times the optimum solution, since P, this capital P, is a lower bound on the optimum solution. And we are done, right? So the algorithm achieves a total profit at least as good as 1 minus epsilon times the optimum profit. So much about the performance guarantee. Now quickly the computation time. Essentially, I explained it already. So remember that the dynamic programming algorithm has a computation time n squared times p, where p is the maximum profit that appears among all the items. And now we have chosen the right scaling parameter k, right? So the new maximum profit value in the rounded instance is this capital P divided by k, which is exactly equal to n divided by epsilon. So hence, if I look at the computation time in the new rounded instance, which would be this one, this P divided by K is N divided by epsilon. And in total, I have a computation time of N to the 3 times 1 over epsilon, which is obviously a polynomial both in N, the number of items, and the desired precision. So great. So what did we achieve? We have derived an FP-task by the simple dynamic programming algorithm for the knapsack problem. So a fully polynomial time approximation scheme. And now the last slide makes the following final remark, namely that the existence of an FP-task, well, that is approximately the same as the existence of a pseudo-polynomial time algorithm. Or in other words, why could we achieve an FP-task, a fully polynomial time approximation scheme for the knapsack problem? Well, because the knapsack problem is only weakly NP-hard, and for strongly NP-hard problems, we cannot expect fully polynomial time approximation schemes, only polynomial time approximation schemes. And let's see how that works. There is a small condition that I have to ask in order for that claim to be really true. Okay, so let's consider a minimization problem which only has integer solution values, which for many of the problems that we looked at is the case. And let's also assume that the optimum solution value on any instance is polynomially bounded in the encoding length of the instance and the largest number that appears in the instance. Okay, so just to make that concrete, think about the traveling salesman problem. Okay, so what is the optimum solution value? That's the sum of the lengths of edges in the graph, right? So that's n edges in the graph, and each of these edges can be at most as long as the maximum length in the graph, right? So the optimum solution value is at most n times c, c being the maximum length that appears in the graph. And that is the sort of polynomial bound that I require here, and it will be fulfilled for many, many combinatorial optimization problems, okay? So the optimum does not have to be polynomial bounded only in the encoding length of the problem, but also in the largest number, which is happening here as well. And under these two conditions, integer solution values and the optimum solution value is not exponentially larger than the largest number that appears. I have the following theorem. If I talk about a strongly NP-hard problem with these properties here, I cannot have a fully polynomial time approximation scheme unless P is equal to NP, because under these conditions, a FP-task, a fully polynomial time approximation scheme, amounts to a pseudo-polynomial time algorithm to solve the problem. And we already know that for strongly NP-hard problems, we cannot have that, right? So final proof of this lecture, let's try to make that at least formal. We fix an epsilon, the precision, such that 1 over epsilon is essentially equal to the optimum solution. Okay, so 1 over epsilon is strictly larger than the optimum solution value, but 1 over epsilon is smaller or equal than the optimum solution value plus 1. Okay, then what can we say about the performance of the algorithm? So our FP-task computes a solution at most 1 plus epsilon times the optimum solution value. Remember, now we talk about minimization problems again. And epsilon times the optimum solution value, by this assumption on epsilon here, is at most 1. It's actually strictly smaller than 1. So that means the performance of our algorithm, the value that the algorithm returns, is strictly smaller than the optimum solution value plus 1. But now, of course, it kicks in that we assumed that we only have integer solution values. So if I have something integer strictly smaller than optimum plus 1 for a minimization problem, it must be equal to the optimum solution. So our fpitas actually computes an optimum solution for such an instance. And finally, what can I say about the computation time of our pitas? Well, by definition of an fpitas, it is polynomial in the encoding length of the problem and the precision 1 over epsilon. But due to our choice of epsilon, this 1 over epsilon is at most the optimum solution value plus 1, and we had the assumption that the optimum solution value is polynomially bounded in the encoding length and the largest number, which means the computation time of our algorithm is polynomially bounded in the input size of the problem and the largest number that appears in the problem. So hence, this algorithm is a pseudo-polynomial time algorithm, which actually computes an optimum solution, and that cannot exist for any strongly NP-hard problem. So that finishes this final proof, which kind of makes clear that we can expect to find fully polynomial time approximation schemes only for problems that are weakly NP-hard, but not for problems that are strongly NP-hard. And that's it. So that was the final proof of this lecture number 12, and the final proof of all the lectures in discrete optimization for this master course. The final technical remark I want to make is that after we have done all the Q&As on all the lectures, there will be one additional Q&A in which you can ask about an example exam that I still have to put online. So let me finish by saying that, well, I like to teach this course. It's one of my favorite courses to teach, and I hope, even though we had these weird circumstances, these weird COVID circumstances this year, I hope you could enjoy the course, the lecture recordings, and also a little bit of the exercises. And for me, it was also a lot of work, so that is good enough for me at least to say good luck for the exam, success for the exam, and nice that you have been with me with this course. Cheers.